Okay, today we're going to be talking about rational exponents, and I want to give a quick review of the exponent rules. Okay, so the first rule is that x to the m times x to the n equals x to the m plus n. Okay, so the reason why this is true, here I'll show this on the next line, I'm going to erase it right after this, but say we have x to the second and x to the third. Oh, sorry, just a second. Okay, so this is the same thing as 2x's and 3x's. So you have x to the second puts these two x's right here, x to the third has these 3 x's here, and there's 1, 2, 3, 4, 5. There's 5 x's total, so you have x to the fifth. So that's just that's just an example of why this works, but this concept works for all real numbers, but in our case we only care about rational numbers. So if you had something like x to the 1/3 times x to the, let's say, well, let's make it 2/3. Oh, whoops, just a second. Had a typo. X to the 1/3 times x to the 2/3. Well, that is the same thing as x to the 1/3 plus 2/3, which is the same thing as x to the first, or x. So let's go over this again. So we have x to the power of 1/3 times x to the power of 2/3. Just like up here, even though these aren't whole numbers, you can still combine them the same way. So you have x to the power of 1/3 and x to the power of 2/3 will give you x to the power of 1, which is of course just simplified to x. Now that's the first rule of exponent rules, but there's still several more to go. The second rule is that if you have x to the power of m over x to the power of n, that's the same thing as x to the power of m minus n. Okay, so the reason why this is true is pretty similar to the reason above. Remember before, we showed how they combined to make m plus n, but let's say we have m to the fourth over, not m, sorry, x to the fourth over x to the second. Okay, so what we have here is a fraction where we have terms that can be cancelled. So you have this x to the fourth can be cancelled and to become x squared, and this x squared will disappear. So this entire thing is equal to x to the 4 minus 2, which is equal to x to the 2. Okay, so that concludes rule 2. Now rule 3, if we have x to the m in parentheses and then to the n outside parentheses, that's equal to x to the m times n. So to show you how this one works, let me scroll down a little bit, and So say we have x squared, but we put it in parentheses to the power of 3. Okay, so this is the same thing as take these two x's and we'll have xx to the power of 3, and that will give you xx, xx, xx. Now, in this case, when you have multiplication like this, you can just remove the parentheses. So that means you'll have 1, 2, 3, 4, 5, 6 x's left, which is the same thing as x over 6. And notice, of course, that 6 is 2 times 3. But again, just like with all of these previous rules, this doesn't just work for whole numbers. This is just an example, but it will still work for any rational numbers. So let's go on to rule number 4, and that is that if you have x times y in parentheses to the power of n, that's the same thing as x to the power of n times y to the power of n. So what we have here is essentially a distribution rule. It's very, very similar to the distribution rule that you have for multiplication for an addition. So you're distributing this n to go to both the x and the y. So to give a demonstration of this one, say you have xy to the power of 3. Okay, so this means xy xy. So that means that we have here, we can get rid of these parentheses and we can rearrange everything. So we'll have xy, xy, xy. But remember that multiplication is what we have the commutativity property, which means that you can just rearrange these in any order that you want. So you could have x, 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 y, y, y. So you have 3 x's and 3 y's. So you have x to the third and y to the third. So notice that now we've had this 3 distributed to both the x and the y. So that is a demonstration of the fourth property. Now the fifth property. I know this is tedious, but bear with me. Eventually we'll get to some examples, and it'll stop being quite so tedious. Oops. Okay, so if we have x over y, the entire thing to the power of n, that is going to be equal to x to the power of n and y to the power of n. Like this. Okay, so we have x over y all to the power of n. Just like up here, the n distributes to the x and the y. So this is something that's going to be pretty important later on, and I'm not going to deal with an example with that. Oh well, it won't be too hard, so I guess I'll go ahead and do it. So let's say we have x over y to the power of 3. Okay, x to the y all to the power of 3. So that's going to be equal to xy sorry, x over y, x over y, x over y, which is going to be the same thing as 3x's over 3y's, which is x to the third over y to the third. And notice that we just distributed this 3 to both the x and the y. So we did it the long way, but we can see that it still works out the same way. So now on to rule number 6, where we have x to the power of negative n equals 1, let's make this 1 over x to the power of n. Whoops, not equals n, typo. Okay, x to the power of negative n equals 1 over x to the n. This one is a little bit more difficult to demonstrate. In fact, I don't think I'm going to show you exactly why this is true. In fact, I would have to kind of think about it for a while myself, because I don't remember off the top of my head why this works out the way it does. It's kind of a technical reason, I remember that much. But I will say it comes as a result of these previous rules. If you play around with these, you'll see why this works out the way it does. But it takes up a lot of time, so I'm not going to bother with it. Best thing to do is just have that one memorized, I think. So then we'll go on to rule number 7, which is kind of an extension of rule number 6. If you have... Let's see if I can get this out pretty fast. Okay, so we have x to the power of negative n over x, oh, make this m, not n. So x to the power of negative n over y to the power of negative m. This is going to be equal to y to the power of m over x to the power of n. So this is kind of similar to the first one. Notice that we have x to the power of n on the top, and it ends up on the bottom. That's really true here too. We have x to the power of negative n on top, then it becomes x to the power of negative n on x to the power of positive n on the bottom. So whenever we have these over here, they just switch places. Now that's going to be hugely important later on. In particular, whenever you have large rational expressions that have negative exponents, you want to be able to move you want to be able to move a factor from the top to the bottom, from the bottom to the top. And related to 7 is 7b, and that is okay. So we've got x. Oh, whoops. I did not do this right. I'm using a markup language in real time, and sometimes it doesn't work out quite exactly like I'd like it to, but it seems to be the best way to do it so far. So we have x over y all to the power of negative n is the same thing as y over x, but all to the power of positive n. See, all I did here was I had this negative sign here, and since there was a fraction on the inside, it's a fraction all to the power of negative n, I flipped the inside of it. So instead of x over y, it's y over x, and now it has a positive n. So that is rule 7b. It's just kind of an extension of rule 7. So this next one, rule 8, is very straightforward. Oops. It is x to the 0 equals 1. Now, we don't know what x is. X could be anything except for 0. 0 to the power of 0 is not something you'll ever see because it's not a real number. But any number except for 0. 1 to the power of 0 is 1. 2 to the power of 0 is 1. 27.96 to the 0 is 1. And The real reason for this is pretty technical, but I can kind of demonstrate it by showing you this. Let's say you have 2 squared. Well, we know that 2 squared is 2 times 2, right? Well, there's also an implied 1 here. So 2 squared is 2 and 2, but there's still kind of this lingering 1 out front, technically speaking. So then if you have 2 to the first, you technically have you still have the 2, but there's also this kind of hidden implied 1. So if you have 2 to the 0, well, the 1 is still there, so it's 2 to the 0 equals 1. There is no number. It's kind of counterintuitive, because you're going to think that it's going to be equal to 0, but there is actually nothing that you can make as an exponent that will make this equal to 0. As long as this x is non-zero, this can never be 0. That's kind of an important property that we'll probably see later on. Now this last property, number 9, is not one we'll see too much in section 8.1 that much, but we will see it quite a bit in the next section, and it is x to the power of 1/2 is equal to, or we could just make this whole thing a fraction. So x to the power of 1/2 is equal to, okay, let's see if this works. I've never actually done a square root before, but cool, it does work. X to the power of 1/2 is the same thing as the square root of x. And we can generalize this a little bit further to say, okay, let's see if I can do this one. X to the power of x to the power of 1 over n is equal to the nth root of x. That kind of makes sense. That n needs to be closer over to here, but the nth root of x, all to the power of 1, sort of. That's actually the specific powers we'll see later on in section 8.2. But as for now, we have the x to the power of 1 over n is the same thing as the nth root of x. So, like if we have 8 to the power of 8 to the power of 1/3. That's going to be so 8. Since 8 is equal to 2. Okay, since 8 is equal to 2 times 2 times 2, that means the cube root of 8 is going to be equal to 2. And that's what a cube root is. It just means that we have 3 2's. See, a square root is if we have, like, the square root of 4 is 2, because 2 times 2, you have 2 of them makes 4. The cube root is because you have 3. 2 times 2 times 2 is 8. Okay, so that concludes the 9 very tedious rules. So now we're done with the tedious section, but they're done with the really tedious section. Now we have another kind of tedious section to do, but I want to say that to simplify any kind of expression with that's the next section, with rational exponents, the first thing you want to do is cancel unnecessary terms. Oops. There we go. Okay, so cancel unnecessary terms, then rearrange so there's no negative exponents. Okay, let's scroll down just a little bit. Rearrange so there's no negative exponents, and combine as many exponents as you can. Okay, so when to cancel unnecessary terms, just like we've seen before, if you have an x on the top and an x on the bottom, and they're both factors, they're not being added, but they're actually factors, then you can cancel them. But you can rearrange them. When we're done with canceling, we rearrange them using Rule 7 or Rule 6, whichever way you want to think about it. Rule 7 and Rule 6 are kind of the same thing, but it's easier to show them separately so that you can see what you're doing more clearly. You want to rearrange them so that there aren't any negative exponents anywhere in the expression, and you want to combine as many exponents as you can. So, as an application of Rule 6 and 7, because hopefully, here, let's put a break here so you can tell that I'm doing something different. Okay, so now feel free to, if this is going kind of fast, feel free to you know, scrub through the video to see what parts are getting missed and things like that. So an application of Rules 6 and 7 is if you have we've got x to the power of m times y to the power of negative n over z to the power of p. And I did something wrong. Oh, here we go. Okay, so x to the power of m times y to the power of negative n over, oops, not x, z to the power of p. Now, to use Rule 6 and 7, you see we have this negative exponent here. Okay, so this negative exponent, let's rewrite this as two separate fractions. So we have x to the power of m over z to the power of p for one of them. So this is our first fraction times y. Let's not even make it a fraction. Let's just make this a separate entity. Y to the power of negative n. So this y to the power of negative n. Well, remember, let's scroll up to rule number 6. So y to the power of negative n will be 1 over y to the n. So that means that this will be equal to x to the power of m z over z to the power of p times 1 over y to the power of n. Okay, so now we can see that this is a we don't have any negative exponents left, but we can go ahead and combine these two fractions, and that'll make it fraction of x to the power of m over z to the power of p times y to the power of n. So you have x over to the power of m over z to the power of p times y to the power of n. But notice something. All we did was move this y with the negative n to the bottom. So we can skip all I mean, as long as we understand the rules, we understand exactly how this is working, we could skip these two steps here. They're not really necessary. So hopefully it won't delete too much by mistake. Okay, I did something wrong here. Here we go. So now we can see that we have x to the power of m over times y to the power of negative n over z to the power of p. That y to the power of negative n can just be moved down as long as it is a factor. This will not work if it's y to the power of n plus. So if there was a plus in between like this, then this would be not equal. So this sign here means not equal. That means that this is a no-no. We don't want to do this. It doesn't work that way. But to go back to the way things were before we have, if we get rid of the plus, because remember, when it's a plus, it's not a factor anymore. In this case, this works out just fine. So the basic idea is, if you have, and I'm going to write this down because this is really important. If you have a single factor with a negative exponent, you can move it to the other side of the fraction bar. Okay, I need to get a line break in there somewhere. And again. Okay, so if you have a single factor, let's move it a little to the right. If you have a single factor with a negative exponent, you can move it to the other side of the fraction bar. This is hugely important to understand, that it has to be a factor. It can't be something that you're adding. But now that I've beaten that dead horse, let's go on to an example. And the reason why I want to go straight into examples is because the best way to understand this stuff is by example, by practice, and by asking questions if you have if there's anything else that you don't understand, so you can go, if you have any other questions, you can ask this in class. So let's say we have three x times y over, to the power of -2 over x to the third. I did something wrong again, but I'm not sure what it was. Let's take a look at the error output. Double superscript. Oh, I see. X to the power of... This is very awkward. There's no power to that x. Okay, here we go. We got it exactly the way I wanted to do it now. So we have 3xy, but all of this to the power of 2. So we have 3xy to the power of -2 over x cubed, all to the power of 2. So the first thing we want to do, we don't want to mess with this 2 out here just yet. We want to kind of leave that until the thing we have on the inside is quite a bit simpler than it already is. So let's say that what can we deal with here? Well, we have these 3's that can, these x's, one of them can cancel out. So here, I'll just copy this over so I don't spend a lot of time typing it out. So let's get rid of this x here. So the x for the top goes away, the x on the bottom changes to 2. So that means we have this 3y to the -2 over x squared, and of course we still have the 2 on the outside. And then we have now to deal with the now we want to deal with the negative exponent up here. So we can say that this whole thing, what did I do wrong? I have another error. Let's see what I did wrong this time. Extra thing to the right. Okay. There we go. Okay, so right now this is still the same thing. But we have this y to the power of -2, so we want to move that to the bottom by saying, making it a positive exponent. So we'll have x to the power of 2 times y to the power of 2. So now we have no negative exponents. So the inside of this is as simplified as it comes. But of course we still have this 2 out here. We still need to deal with that. So let's go to a new line, and we'll have that sorry, just a second. Going to copy it over. Okay, so we want to distribute this 2 to the inside of the fraction. So that'll give us, let's not copy it, let's just start from scratch. So we have 3 to the power of 2 over x to the power of 2 times y to the power of 2, and that entire thing to the power of 2. Okay, so this 2 is distributed to both top and bottom. I forget which rule that is. It looks like it's rule number 5. So this 2 goes to both the 3 and to the bottom. And notice that it goes to the entire bottom. So now we have to go to the 2 is going to distribute both to the x squared and the y squared. So that means that this next part will be, okay, first of course, what is 3 squared? Well, it's 9. So we have 9 over, and let's finish this up. We have x squared and y squared. So this 2 was distributed to both the x squared and the y squared. So we get 9 over x squared times y squared, which is going to be equal to, whenever we, okay, so now we have rule number 3, where we have an exponent on the outside of parentheses. So we have 2 times 2 will be 4, so we have x to the power of 4, and we still have that y to the power of 4. Oh, okay, sorry. So we have 9 over x to the power of 4 times y to the power of 4, and this is as far as it can be simplified. So this is going to be our final answer for this example. And let's go on to, oh gosh, let's go on to another example. Okay, it looks like we're getting to the end of the page, so I'm going to get rid of everything above. Let's see. Okay. And move back up to the top. Okay, so we have, for this next example, this is going to be a little bit shorter, but still not extremely short. So we have 4x over y cubed, but the entire thing to the power of -3. Oops, just a second, sorry. Okay, so we have 4x over y cubed, the entire thing to the power of -3. Well, my first instinct is, oh, well, I want to distribute that -3, and that will work. But before we even do that, remember rule 7b. We have this negative exponent here, and we have a fraction on the inside. So we can just flip the fraction to get y cubed over 4x all to the power of +3. Oh, sorry, let me put in the parentheses. Okay, so y cubed over 4x all to the power of +3. That makes this a lot easier to deal with. So now we can say that this is equal to y to the third over 4x to the third. So the 3 distributed to the y to the third and to the 4x to the third, no, not to 4x to the third, to the 4x, sorry, to get y to the third over 4x all to the third. So y to the third, well, remember rule number 3, where we multiply these two together. So we'll get y to the 9th over, and then we still have this 4x to the third, where we'll get 4 to the third. I'm not even sure what that is. So I had, okay, 64. 4 to the third. 4 times 4 is 16. 4 times 16 is 64. And then we'll still have the x to the third. So we have this 3 went to this y to the third, all to the third, to distribute to make y to the ninth. And then 4x to the third. Well, this 3 went to the 4 and made it 64. Then it went to the x to make it x cubed. So this is the most simplified form of this particular example. And there's one more example. Not one more, actually. One more example that's kind of like this. I mean, after this example, we go on to something that's a little bit more complex. So, this example is... Here, let's scroll down to it. We have x to the power of 5, 6 all to the power of 3. Okay, so x to the power of 5, 6 all to the power of 3. So remember from rule 3 that this is equal to x to the power of 5, 6 x to the power of 5 over 6 times 3. Now that times 3 is in the exponent there. I don't know how clear that is, but that 0.3 is in the same line as 5, 6, not x. So that means that that's going to be x to the power of 15 over 6. And 15 over 6, you can reduce that to... you can take a 3 out of each, and you'll have a 5 on top and a 2 on bottom. So you'll have x to the power of 5 halves. And this is the most simplified form of this particular problem. So that is as far as this goes, but let's do another example. This is a bit more complicated, but let's see how far we can go. So it's a big fraction, of course. A lot of these problems are going to be fractions. We have 16a to the 5th times b to the negative 2 over a to the power of negative 1 times b to the power of negative 6. And I did something wrong again. Okay, if you've ever coded with HTML, you know why. I mean, I'm not using HTML. I'm using something different called latex. And HTML, you know, sometimes you type something up and you think, why did it not come out the way I wanted it to? It's kind of the same way with this. So that's why sometimes I get some weird stuff going on. So we have 16a to the 5th times b to the negative 2 all over a to the negative 1 times b to the negative 6. Okay, hard enough already, but let's make it a little bit harder and add something to the outside of it. So the whole thing to the power of 1/2. So now we can well, our instinct is to distribute this out, but before we bother with that, let's take a look at the inside first. Now, we have a lot of negative exponents here, so we can deal with that pretty readily. Let's just flip them all so that we don't have any negative exponents left. So we have, let's see, if we have 16, we're still going to have that. This a to the 5th is still going to be on there, so a to the 5th, but we're also going to have this a to the 1st and this b to the 6th, so a to the first and b to the sixth is going to be on the top as well. But then this b to the negative second is going to come down to the bottom. So I misspelled something. One of these commands. Okay, so this a to the fifth stays where it is, and so does the 16. Everything else switches. This a to the negative first comes up here. It becomes a to the first. This b to the negative 2 goes down here. It comes b squared. This b to the negative 6 comes on top. It's b to the power of 6. So beyond that, we can terms that we can combine. Oh, of course, and all of this is still to the power of 1/2. Don't forget to put that 1/2 up there. So after this, we have terms that we can combine. Remember, the very first rule was that x to the power, let's see, I already deleted it, but we have x to the power of m, let's see if I can copy it down here, x to the power of m times x to the power of n equals x to the power of m plus n. Okay, so remember this rule down here. We can use that to work with this, the a to the fifth, a to the first. So that means that a to the fifth, a to the first will become, okay, we're still going to have the 16, and we're still going to have the b squared on the bottom. So I'm going to go ahead and put that on the bottom right now, just so we can see it. Just so we can see the actual fraction, because otherwise it's going to give me an error. So this a to the fifth times a to the first is going to be a to the 5 plus 1, or a to the 6. And then this, we still have this b to the 6 as well. Oops, that's on the outside of the fraction. B to the 6. Okay, so we still have this b to the 6th right here, and this b squared, but also remember, of course, that we still have the to the power of it's still to the power of 1/2. So now we can more easily see that there are some unnecessary terms that we can cancel. Now, technically speaking, this is also the same thing as rule 2. We have b to the 6th over b squared. B to the 6th minus 2 is 4. Or we can think of it as just we have 2 on the bottom and we have 6 on top, so we can cancel out 2 of them. So that means that this is equal to 16 times a to the 6th, b to the 4th, over 1. But of course, don't forget, part of the reason why I'm actually saying that out loud, don't forget to put the 1/2, is because I'm reminding myself not to forget the 1/2. It is very, very easy to let something like that slip by you, especially when you get into something more complicated, like trigonometry or something. Some of these little things, if you forget to bring them down with you, they'll come back and haunt you. So, the b squareds have been canceled. B squared has been canceled out, and we have 4 b's left on top. Now, this is an we can just rewrite this as an understood one. Let's just get rid of it. So we have, instead of a fraction, let's just get rid of. Okay, so now we just got rid of the understood one because it's unnecessary. And now we are in a position where we can distribute this 1/2 to the 16, to the a squared, and the b squared. So this is 16 to the power of 1/2 times a to the 6th, the power of 1/2, and b to the 4th, the power of 1/2. And I did something wrong. What did I do wrong? I see. Okay, so the 1/2 distributed to the 16, to the a to the 6th, and the b to the 4th. So now we have 16 1/2, a to the 6th, to the 1/2, b to the 4th to the 1/2. Okay, so now we can just go ahead and simplify each of these individual factors. So 16 to the 1/2, remember that is just based on Rule 9, is just going to be 16, the square root of 16, which is 4. So let's scroll down a little bit more. So the square root of 16 is 4. So the next thing, a to the power of 6 to the power of 1/2, we just multiply these two fractions now based on Rule 3, and we'll get a to the power of 3. And for this next part here, we have 4 times 1/2, so we'll just get b to the power of 2. So we have 4a cubed b squared, which is quite a bit simpler from our original expression, this gigantic mess here. So that's why we call it simplifying, obviously. This will be our final answer for this particular example. Okay, we have one more example, and this is kind of a strange one. That's why I want to do it, just because it's strange. So we have 16 to the power of 3/4. Okay, so 16 to the power of 3/4. Now you can see immediately that you can make this the cube root of 16 quantity cubed, and that'll work just fine. But I want to show you a different way of doing it. So just because I want you to see these rules of exponents in action. So what is 16? Well, 16 is the same thing as 4 squared, right? Not 4 to the power of 12. 4 squared. And of course this whole thing is still to the power of 3/4. So 16 is 4 squared, but what is 4? 4 is 2 squared. So we can write that as 2 squared forgot a parentheses, all to the power of 3/4. So now we've sort of expanded this out in kind of a strange way. So now we can combine these two numbers to make this equal to 2 to the power of 4 to the power of 3/4. So now we're almost done simplifying. So now we just, by Rule 3, will combine this exponent and this exponent. So we'll get 2 to the power of, and 4 times 3 is 12, so it's going to be 12 over 4. Now what's 12 over 4? Okay, let's go on to a new line, and 12 over 4 is 3, so this whole thing is equal to 2 to the power of 3. Well, 2 to the power of 3 is just 8. So that means our final answer in this case is 8. And you probably wouldn't have guessed, before you knew all these rules, if someone said, what's 16 to the power of 3/4, you would have thought, well, I don't know. Because that's kind of, it's kind of a strange thing. You don't see that too often. But it's simplified into just one simple number, 8. And I think that's kind of interesting. But for now, that is the last example for rational exponents that I have. But we'll see if we go on to, if I make another video for the radical expressions and functions section. So long for now.